Okay, good morning, everyone. You can put your mic on and you can talk to me. Good
Good
morning.
morning, Prof.
Good morning,
Good
Matthew.
morning, sir.
Good morning,
Prof.
Aaron.
Morning, Prof.
Morning, TK. Morning, Gaurika.
Morning, Prof.
All
Morning,
right.
Prof.
Morning, all sort of. Morning, Ambika, Adrian. All right.
Morning, Prof.
Okay, Kevin. Okay, what we are going to do today is we're going to finish off the 2018 paper. We did up to problem 20, I think, and we've got a few more left in that. And after that, I've chosen some problems, which are logical kinds of problems, and also problems on games. Very often in round 2, they ask questions on games, on what is the best strategy to win. So I don't know whether it's round 2 or round 3, but whatever. We will do those kinds of problems as well. So we have some rather challenging problems today, and some of them will take a fairly long time to unravel. So I sent you a note. Those of you who read it will know that I asked that for you to stay on a little bit past 11 o'clock because we want to finish all the problems. And I'm not going to rush through them so that you will have a good chance to understand the solutions. Okay, because some of them are quite demanding and they require a certain amount of thought. All right, so let's get going with this. Okay, can you all see the screen now?
Yes, Prof.
Okay, good.
Yes.
Okay. All right, the very first problem, and I'm going to assume that you all had a chance to look at the questions. I must apologize. I actually was hoping that you will see the questions from Wednesday, but they were only put on, became available yesterday morning owing to some glitch. So you didn't have much time. Okay, let's now do problem 21. Problem 21 says 3 carpets have a combined area of 200 square meters. Now that means that if you put those carpets along side by side, then the full area is 300. I'm sorry, 200 square meters. But if you overlap them, if you put one carpet, not necessarily on top of each other, but sort of so that they share some areas, then the total floor area is 140 square meters. And the area which is covered by exactly 2 layers of carpet is 24 square meters. So you've got 3 numbers here. You've got 200, which is the sum of the areas of the 3 carpets. If you separate them, you get 200. But when you put them on top of each other, then the area that they cover now will be 140. It'll be smaller because some areas will be repeated. And then they give you one further information that the area covered by exactly 2 layers of carpet is 24 square meters. Okay, I'm going to go to my whiteboard because I will need much more space here. So let me go to my whiteboard and share the whiteboard with you. All right. Can you all see the whiteboard now?
Yes, Prof.
All right, good. So I'm going to draw the 3 carpets. We'll just assume that they all are circular. Doesn't really matter. So you got one carpet here like this, and another one which intersects. Let's make this intersect also. All right, so you got these three carpets, and you are told that okay, you're given lots of three pieces of information, but if you look at these three carpets, there are lots of spaces here. Okay, uh, we won't give the carpets any names, but what we will do is we will give names to the areas that are covered. All right, so suppose we take this A, B, C, the ones on the outside, and then we'll make this P, Q, R. And the question, I forgot to mention the question. The question is, what area is covered by exactly three carpets? Now you'll see this part here. This part here is the area that is covered by exactly three carpets. Right? This is covered. This area is covered by that one as well as that one. So this is the problem. What is the value of x? Okay. And what are we given? We're given that the area covered by exactly two carpets. Now let me just unpack this diagram. You see, this A here is the area covered by this carpet. Well, let's give names to them. Carpet X, Y, and Z. Right? This area is covered by X, but not by Y and not by Z. I'm talking about area A. Likewise, B is covered by only one carpet. So the area covered by X is B, and that area is not part of the other areas. So you've got A, B, and C are each areas covered by exactly one carpet. I'll repeat that. A, B, and C are areas covered by exactly one carpet. Let's put that down. Area covered by exactly one carpet. Sorry for the scrolly writing. Okay, we're going to call that is A plus B plus C. Let's call that Z or Y. So the area covered by three carpets is X. Oh, okay, listen, we might as well call it Z. And then the area covered by two carpets, so P will be the area covered by exactly two carpets, likewise Q, and likewise R. So the area covered by exactly two carpets, and this is how we know that the area covered by exactly two carpets, that is 24. We'll call that Y. So Y is the area covered by exactly two carpets. I'm not going to write it in full. So Y is the area covered by exactly two carpets. Z is the area covered by exactly one carpet. And as we saw, X is the area covered by all three carpets. Okay, so I've got names to these three things. We already know that the area covered by exactly two carpets is 24. So we know the value for Y. Right. Now here's something important. We were told that the total area of the three separate carpets is 200. Right? So what is 200? The 200 will be okay, we'll just hold on with that. Let's just first see what is, we had another number, 140. And 140 was this area here. the area covered by these three carpets when they're put into this. So if you analyze 140, it is made up of three parts. It is that area which is covered by exactly one carpet, the area covered by exactly two carpet, and the area covered by exactly three carpet. So 140 is actually x plus y plus z, right? Because that will take care of all the area covered by these three carpets. Those which cover one, those which cover two, and those which cover three. And we already know y. Y we know is 24. So remember, we need to find x. So I'm getting equations now. I've told you many times that in mathematics you tried, x plus z. Okay, there's a 24 here. I take the 24 to the other side and I get 116. So I got an equation with two unknowns, x plus z. Now the question is, can I get another equation involving x and z? All right, now we know that 200, let's put it down here. 200 is the area of the three carpets if they are separated. Now let's have a look at this and see what happens. You see, if I separate them, then I will have A plus B plus C, that's the area covered by one carpet. But the area covered by two carpets is Y, okay? Right? Y is the total area covered by two carpets. But if you want to separate them, right, then you'll have to get 2Y when they are separated, because they're all on top of each other. You see, these, they're on top of each other. Q and there's something underneath it. Q and something underneath it. So when you take them out, then you got two of these, right, to give you the area when they are separated. And likewise, this area X is counted three times. Maybe that's a better way of looking at it. Oh, I'm sorry. This is Z. We said that this is Z. Area covered by one carpet was Z. And the area covered by three carpets was 3. So that area X has to be counted 3 times, Y has to be counted 2 times, and this has to be counted once to get the total area when you separate them. So now that gives you, this is 48 here. And there you have another equation. Let's write this equation. It's 3x plus z equals, you take the 48 and you put it to the other side. It's 200 minus 48. 48. And which is 152. And now we can find x. The problem was to find x. And you got two equations and two unknowns. You can find x by eliminating z. So you subtract, right? You subtract the smaller from the larger. 3x minus x is 2x. Subtract, that's why we subtracted, because the z will disappear. And you get 152 minus 116, and that is 36. So 2x is equal to 36, and therefore x is 18. And this is the area that is covered by all three carpets. So the answer to the problem is 18. Right. So that was quite a challenging problem. It took almost 20 minutes to solve that problem. Let's get on to the next one. The next problem is, what is the next problem? Okay, so I'm here now. Um, okay, now we go to problem 22. Right? The 2018 problems were quite hard, I must say. Um so this problem here is a problem on probability, and you are only exposed to probability in grade 12, and I think some of them will start in grade 11. Um, so let's have a look at this. Probably it'll be a nice, good lesson on probability. See how you do problems on probability. Okay, you got teams A and B are playing a series of games against each other. Okay, so you got some games. We don't know soccer or whatever. The probabilities of either team to win any game are equal. Well, what we are saying is that A and B have got equal chances. Any game, it's neither here nor there. Anyone can win. In probabilistic terms, it means that the probability that A will win is 50% and the probability that B will win is 50% or half. The probability that A wins is half. Probability is a fraction between 0 and 1. Remember that. It's a fraction between 0 and 1. So the probability that A wins is half. The same would be. Okay, now either team must win 2 games or team B must win 3 games to win the series. Okay, so we are at the last end of the series. And if A win 2 games, A will win. And if B wins 3 games, it'll win. Now, question is now, if the probability of team A winning the series is expressed in simplest form. I told you it's a fraction, which will be between 0 and 1. And if you write that probability as x over y, that A wins, calculate x plus y. Okay, so this is quite a challenging problem. And let's unpack this thing. Let's unpack it. Now let's see what happens here when we, okay, there's nothing much to remember here. All we must remember, if A wins 2 games, A wins the series, and B wins 3 games, it wins the series. So I'm going to move over to my whiteboard, and those are the only information that I need to carry over to my whiteboard, that if A wins 2 series, it wins if A wins 2 games, it wins the series. Okay, now suppose they play and we'll play, we're going to say, suppose they play the first game and B wins. I'm going to put B like this in front to show that B won the first game. And suppose B won the second game also. Right, what is the probability of B winning the first game? It's a half. So half the time, B will win. Right. Now, for B to win the second game as well, right, it'll mean that it's half of half. Because here, to get there, it was half. And here, it's to win this game as well, it's half of half. So what we are saying is that the probability for this particular pair to occur is a half times half. And that's a quarter. And this is very crucial. When you got a particular sequence of winning and losing, suppose I had A, B, A. What is the probability that this particular sequence occurs? Which means that if A wins first game, B wins second game, A wins third game. What is the probability that this particular sequence occurs? It is a half times half times half, and that is 1/8. Right? So this is an important aspect of probability, right? That when you have the probability of one thing happening, and then with that happening, if the probability of another thing happening, then you have to multiply the 2 probabilities to get the probability of both things happening simultaneously. Okay, now that was quite a mouthful, right? But you understand what I'm saying, that if you want AB, then the probability of this particular AB occurring is 1/4, but the probability of this occurring is even smaller, so it's 1/8, you see? It's either ABA or ABB, see? And then if you had another B here, that's another 1/8. So it's either A or B. So if you add the two, you'll get a quarter. 1/8 plus 1/8 is a quarter. And that is the probability that AB occurs. Okay, now, what are the situations? You want A to win, remember? Okay, so if you want A to win, I'm going to just clear out this thing here. Hope you understood what I said there. Okay, I want A to win. Now let's see all the possibilities. Suppose A wins the first game, right? If A wins the first game, there are two possibilities. Either it wins the second game or loses the second game, in which case B wins. Okay, now I'm going to take the case where A wins the second game as well. Now, the moment A wins the second game, it's finished. The tournament is over. Nothing more to report. And the chances that this happens is a quarter, half times half. If there are two symbols, it's quarter. If three symbols, it's 1/8, and so on. Okay. All right, so this is the first possibility. But suppose A wins the first game, but B wins the second game. So the game is not yet over. Right? Now, when this happens, you will have. So let's put it this way. We want to count these. So we will have it in three different stages. I'm sorry, let me repeat this thing. Right. We want to count it in a proper way, and I'm going to do it like this. B wins no game. B wins one game. And B wins two games. Now, B cannot win three games because we want A to win. The moment B wins three games, then B wins, right? So the only three possibilities, either B wins no game, B wins one game, or B wins two games. Now let's take each of those sequences here. If B wins no game, then it means that A won both games and the game would have stopped right there. The tournament would have stopped right there. Okay, let's hold on with that. B wins one game. We could have B winning the first game, but B wins one game, so B wins. A will win the other two games. Okay. Now, if B wins one game, you could have had A winning the first game, but you can't have A winning the second game because that means we are going to that one. We want B to win at least one game. So we have to put a B here, right? But B wins exactly one game, so it stops there. Here now, A wins two games, so that's a possibility. So B can be the first position, the second position, but B can't be in the third position. That's the important thing, because otherwise you'll have AA. You can't have AAB because the moment you have AA, the tournament is over. So let's take the other case where B wins two games. So you have A. You can't have another A next to it. So you'll have to have a B. And B wins two games. So you could have, you can't have an A here. Otherwise, it's over, right? And when you do this, you've got that. So B winning two games, it's like this. If A wins the first game, this is the only possibility. You can't have A here, right? You have to have B. And you can't have A here. Otherwise, the tournament is over and B has only won one game. I'm saying B wins two games. So you have to have a B here. And here, you can't have a B because you want A to win. Okay. Or you could have B winning the first game, in which case you're going to have this, and the supporters of B are thrilled. Now they say, oh, we won the tournament. But They didn't know that A was coming from the back. So A will have to win. B wins 2 games. So A will have to win the last 2. That is a possibility. Or B wins the first game and A wins the second game, but A can't win the third game because otherwise we want B to win 2 games, you see. So B will have to win this game and you can't have B here. You'll have A. So those are the only possible cases. See? You can't have B winning 3 games. So what is the probability of the first one happening? The probability of the first one happening is a quarter. The probability of this, each one is 1/8. So here you have 1/8 in one case, another 1/8 in another case. In this case, here is another 1/8. And here too, the probability of the first one happening, but now there are 4 of them, so it's half times half times half times half. So it's 1/16 plus 1/16 plus 1/16. Probability of each one happening is 1/16. So you add up all these probabilities, and now the final answer is, these are the only cases. So the probability that A wins, we've taken all the possible cases where A wins, right? You add up all these things and when you work it out, you'll see it's 11/16. And that is the probability that A wins is 11/16. Just remember that. So if I go back to my original question to see what the question was, share the screen. If the probability of A winning the series is expressed in simplest form as x over y, so here you got x over y is 11/16. That's the simplest form. That cannot be simplified any further. So you got that x over y must be equal to 11/16. And the question was, what is the value of x plus y? And that is 11 plus 16, which is 27. So the answer to this question is 27. As I said, it's a hard problem. It's the kind of problem that even in metric papers, grade 12, it wouldn't occur because it's quite a challenging problem. But I hope you learned something from this. Study it carefully. You'll see how you deal with probability problems. Sometimes you add, sometimes you multiply. And you have to understand when you add and when you multiply. Okay, in this case, we added several times, we multiplied several times. So you must ask yourself, when do you multiply and when do you add? Okay, so let's go on to the next problem. We're going to problem number 23 now. Okay, this is problem number 23. Problem number 23 says that you got a multiplication. In the equation, you got an equation here like this. Each of the letters represents a different digit, right? From 0 to 9. But when you multiply these two, this is a 2-digit number, this is a 2-digit number. It could be a 1-digit number because 0 is allowed. Okay, you get this thing here. So the question is, what's the value for E, M, T, and Y? You need to know that because the question says you have to add the 4 numbers. And how do you add the 4 numbers? You have to know each one of them. So let's try to find out what these numbers are. Now the interesting thing here is that this is TTT, like this is like 555 or 777 or whatever it is. So, but this is, well, if it's 555, it's 5 times 111. If it's 777, it's 7 times 111. So this is T multiplied by 111, right? 888 is 8 times 111 and so on. Right, so I can write this as a multiplication sum, So, but this is a single digit here, t. I want it to be 2 digits. So observe that 1113 goes into that. So if you take the 3 out from here, you get 37, and then you multiply that by 3. So you multiply this by 3 and divide that by 3, and you'll get the same product. So you get 3t times 37. And there you have it, because now you've got two-digit numbers, and you can see one of the letters. So you've got the second digit repeats here, you see? Right. And we know the second digit for one of them, that is 7. So this number here, has to be 7 in both cases. Right? And here it's 37. So it's 37 times something equals TTT. All right. But now 3T is the other one. So this 3T ends in 20 in E. So for 3T to end in E, we know what E is. Sorry, I keep making mistakes. 3T ends in 7. Right? You can see. So T will have to be 3. This is 3 times T. This is 3 times T. It ends in 7. So T will have to be 9. That's the only number. 3 times 9 is 27. So T is 9. So there you have it. This is 9. And this is 3T times 37. 37, and you have all the numbers now. E, M, T, and Y are 9 and 2 and 7. Oh, 27 times 37 and 3. Those are the 4 digits which are occurring here, and you need to add up all of them to get the answer. All right, we're not going to waste our time with that. Okay, so that's the way to solve that problem. It's a logical problem. Again, I'll just repeat, the clue is here, and this can be written as a product of 1 digit times this number. This is the key number here. And then you say, okay, I need to multiply 2 numbers to get to this. What are the possibilities? Let's factorize this. It's 3 times 37. There it is. You've got 1 2-digit number. And the 3t will have to be the other number. So it's 37 times something gives you this TTT, and you proceed with the logic beyond that. All right, so let's get on to the next one, 23. All right, let me talk to you guys now. You can talk to me. Pause share for the moment. Now, by show of hands, how many of you got, we did 3 problems, or is it 2? Yeah, 3 problems. How many of you got at least 1? Oh, there are quite a lot of people. We've got 71 participants here. All right, so you got at least 1. Well, that's good. You're in the upper bracket here, between the 21 to 25. And how many of you got 2 of them out? Okay, 2 out of 3. Excellent. 18 people got 2 out of 3. Well done. Okay. I wonder if anybody got 3 out of 3. I'd like to know who the top people are. Ah. Mangolpe. That's good. All 3. Okay. All right. So let's get on. We go to the next problem, number 24 now. Let me see what problem number 24 has for us. Problem number 24 is a geometry problem. Okay. Maga, are you there in the class? Maga is a very good friend of mine, and we enjoy
Yes,
talking.
sir.
Right,
Yes,
okay.
sir.
Maga and I, and Shan, who is also another person who's sitting in today, we are all great fans of geometry, and every now and then we take a challenging geometry problem and we try to solve it. Now, this one here is problem number 24 of 2018. It's quite a challenging problem, and there are a couple of ways of doing it, and I'm going to now tackle this problem. Right. All right, so let's have a look at this problem. What it says is that you've got a right angle triangle, isosceles triangle. So there it is, ABC. It's isosceles, AB equals AC. So these angles are 45 degrees. Angle B and angle C are 45 degrees. Let's bear that in mind. E is the midpoint of AC. Okay, so it means that you've got these are equal. And F is a point on BC such that EF, so from here now, where this meets here, you draw a perpendicular and it hits AC somewhere, and that's F. So you got a 90 degrees here. They give you the values of AB and AC. It's 40 times square root of 3. Now, obviously, these numbers will be used in the calculation. A good trick I always use is I don't like working with all these horrible things. I give a symbol to this. Much easier to work with symbols. So I'm just going to call that A. And I'll do everything in terms of A, and I'll substitute for A right at the end. It's a very neat way of avoiding horrible calculations. Put some symbol to it and substitute at the end, not carry it all the way like heavy baggage right throughout your problem, right throughout your solution. Right, so AB, the sides are A, so this whole side is A. Oh, but then each one is A over 2, and I don't like fractions. So let's make this thing 2A. See, now this is a neat way of avoiding fractions. So we'll say AB is 2A. So A itself is 20 root 3. And now I can put, nicely, I can put an A here, and I'm going to put an A here, put 2A. And that avoids all the root 3 and all that horrible notation. Okay. Now, what is the question now? The question says, what is the area of triangle? Remember, A is a known number. What is the area of triangle CEF? So this is the area, CEF, that we are investigating. What is that area? Well, since you know AB and AC, we know the area of this large triangle. I'll call it the mother triangle, right? Area is half base times height, and the area of ABC, we'll just record that. That we know. It's actually a half base, which is 2A, times height, which is 2A. So in terms of A, the half and the 2 cancel, and you get 2A squared. Right? But remember, A is 20 root 3. So this is 2 times 20 root 3 squared. Right? A is 20 root 3. Now root 3 times root 3 is 3. And 20 times 20 is 400. That's 800. 400 times 2 times 3. And that is 2400. Because root 3 times root 3 is 3. So the area of triangle ABC is 2400. I'm just recording that because I know the area of the large triangle. Now we need to calculate the area of the small triangle. And so what else do we know here? Okay, just remember we need to find that area there. I'm going to remove that little dirt that I put down here, take that out. And So when you think about this, you say, well, I can find the area of this if I know this angle and if I know that side. Oh, I know this is 45. Okay. So the area of this, if you use the formula, area of a triangle, this is a very useful formula. Area of a triangle is half AB sine C. Okay, the great tens, right? Just remember, this is the area of a triangle, where A and B are two sides of a triangle, and C is the angle included by these. The area, if you got two sides of an included angle, you can find the area. It's half the product of the sides times the sine of the included angle. So that's a useful formula. And we're going to use this formula. And so if you know this, well, you got a right angle triangle here, and you got another right angle triangle here. So this triangle should be known completely because you got the two sides. But we can't really work out the angles. But if I call this angle here theta, right, then I can see the tan of theta is A over 2A. So I know tan of theta is a half. So which means I can calculate the area of this triangle because oh, by the way, we know the hypotenuse also. The hypotenuse for this triangle is A. Square this, you get 4A squared. Square this, you get A squared. Add them, you get 5A squared. 4A squared plus A squared is 5A squared. And this, by Pythagoras, is the square root of 5A squared. Square root of A squared is A, and this is root 5. So you could get that as A root 5. And then you say, well, so in this triangle here, I know this, and I know 90 degrees. I know everything in this triangle. But here I don't know anything. Oh, okay, I know at least one thing, and I know 90 degrees, right? But now this thing here now plays an important role here because I don't know what this is. If I know what this is, that one there, let's call it B, then I can calculate the area of this. And I know the area of the whole thing. So I can calculate that. And also, I will know the area of this small triangle. It's half AB times sine of this angle here. Now, this angle here is crucial. If you look carefully, you will see that this angle is related to theta. Because from here, you can go down here, you get 90 minus theta. And this is 90. So this angle here, these two angles add up to 90. Right. So therefore, this angle must be theta. So this dot here is actually theta. Let me just take these things out. The dot is theta. The reason, another way of expressing this is, if you look at this angle, or look, otherwise, if you look at this angle here, it's 90 minus this angle, because the whole thing adds up to 180. There's 190 already, but 90 minus this is that. So this is 90 minus, so this angle is theta. Okay, and I know something about theta. I know that tan theta is a half, you see. So that's very useful. Okay, so now that allows me to calculate the area of CEF. The area of CEF. If I use my formula half AB, I actually named these as AB here, half AB sine theta. That's the area of this. And sine theta, okay, I've got sine theta here. Sine theta is opposite the right angle triangle over hypotenuse. So sine of theta, I can replace it by A over the hypotenuse, which is A root 5. And the A's cancel. So the sine theta is 1 over root 5. So tan of theta is a half, and then therefore you can calculate sine of theta, right? And it's 1 over root 5. So it means I've got half AB and 1 over root 5. So the numerator is AB, and the denominator is 2 root 5. It's 1 over root 5. So the area of CE is AB over 2 root 5. I know what A is. Now the question is, what is B? So you have to look at this triangle, try to see what is B equal to. Okay. Now, do I know what information do I have? B is in this right angle triangle here. I got a 90 and I got one side, but do I know anything else? I need to have three things to know a triangle, right? So I've got 90 and I've got this. Yes, I know, because this angle here, remember the entire was 45? So this angle here is actually 45 minus theta. This angle here. Okay, so we've got this angle is 45 minus theta, which means that in this right angle triangle here, I need to calculate B. So all I have to do is, it's B is your unknown side, and put it over a known side. I always like to use that language. Unknown side over known side, which is A root 5. Remember, A is known. And that is equal to what ratio of 45? It's tan of 45 minus theta. Okay, now we've got tan of 45 minus theta. We are now right in the thick of grade 12 mathematics, or grade 11, or whatever. And you got I'm getting rid of all these because I just want to know that the area of triangle ABC is 2,400. I don't want to go to my whiteboard yet. Now tan of 45 minus theta. Now this thing here, unfortunately, they've asked this question. It's not in the school syllabus, which is not very fair. But you can say tan is sine 45 over cos 45. And sine of a minus b, we have got a formula for that. That's, I think, it's in grade 12 mathematics, sine of a difference and also cos of a difference. So you can put this in a sine of a cos and you have a formula for it and you can calculate it. But there is a very neat formula for tan of a minus b. That is why I cleared the space. Very nice formula. Look at it. It's tan a minus tan b. Most novices will say, oh, tan of a minus b. It's tan a minus tan b. Wrong. It's actually, there is a tan a minus tan b, but it's the numerator of a fraction. And here the denominator is 1 plus, the sign changes, tan a times tan b. Right? Okay, so what does this mean? So here I've got tan 45. The numerator is tan a minus tan b. What is tan 45? I hope you know. It's 1 minus tan 45 minus tan theta. Well, we know tan theta. Oh yeah, there it is. I didn't take it out. It's 1 minus tan theta. And the denominator is tan 45, 1 plus tan 45, tan theta. And tan 45 is a half, 1, and tan theta is half. Now you have a nice, beautiful fraction here. Half over 3 over 2, and that is 1/3. Right. So now that is beautiful now, because now we know that b over a root 5 is 1 over 3. So you can work out what b is, right? You just have to multiply both sides by a root 5 over 3. So b is equal to, okay, I'm going to, that's my answer here. Area of triangle CEF, FCE. We're trying to calculate that. And I had this thing here on hold. So I know that b over a root 5 is 1/3. Let me just put a line here. And this is equal to, I've got ab over 2 root 5. Let's isolate the a over 2 root 5. And b, what is b? b is, cross multiply here, it's a root 5 over 3. So b is, you multiply by a root 5 over 3, and there you have it. I've got my area. Now everything is in terms of a. Happily, the root 5 is cancelled off, and 2 times 3 is 6. So you have a over 6. Oh, wait a minute. You got a squared over 6. You got a squared over 6. And we know what a is. A, remember a is 20 root 3. 2a was 40 root 3. So a is 20 root 3. And when you work this thing out, you get a beautiful answer. It's 200. So the area that we're looking for is 200. Right. You'll all admit that this is not an easy problem. But if you do it step by step and use the form, see, it uses a lot of information. The area of a triangle, of AB, sine C, the ratios of right angle triangles, sine, cos, tan, and so on. It also uses tan of a difference of two angles. So it uses a lot of information. Also the area of a triangle, and so on. So this is quite a challenging problem. Now, but I have another solution. I have another solution, which is not like this. So I'm going to clear these drawings. And I'm going to give you a second solution, which involves only geometry. And it doesn't, only grade 10 geometry is as much as we use. So it's going to be, maybe not. It uses some bits of geometry. All right, so the problem is to find the area of triangle CEF. And the way to do that is, I'm going to perform a construction. As it stands, if I try to calculate it, I wouldn't be able to do it. I need to find a construction. Right, and that is the challenge. My friends, Maga and Shan, we often try to say, what is the construction which will solve this problem? And usually we try various kinds of things, right? But if you use a little bit of logic, remember, we had these two are equal. Okay, we know those two are equal. And we've got, need to find the area of this. And I'm going to do something here. I'm going to use this side here and draw a line from A. I'm going to draw a line which is parallel to EF. Because I suspect that when I do that, I can use the midpoint theorem. See? And also when I do that, I've got a nice 90 degrees here, because this is 90 degrees. So drawing a line parallel like this, it allows me to make some headway into this problem. All right, so let's see what the actual headway is. Let's now look at this new situation and see whether we can calculate this area having this diagram. In the first case, I've got, this is 90 degrees. Okay, why? Because this is parallel. Okay, so there's 90 degrees here. And another thing that I know is that these are equal. But the midpoint theorem, there's a triangle here. E is the midpoint of this, and this is parallel to that. And therefore, by the converse of the midpoint theorem, these two are equal. Let's call these things x. X here, so you got xx. Now be careful, don't think that this is 2x. It isn't. We don't know what this is. Right, so that's an unknown. Let's give a name to that. Let's call it y. Because we know we can't calculate the entire hypotenuse. So we can write an equation, 2x plus y, because the entire hypotenuse can be calculated because we know the other two sides. All right, now there's another important thing here is that I've got this triangle. You see, in the midpoint theorem, so one of the things that comes out from the midpoint theorem is the following, and it's very useful. Just watch. It's a nice, useful thing to know. If you've got, the midpoint theorem says that if you join the midpoints of two sides of a triangle, if you join the midpoints of two sides of a triangle, then this line here is parallel to the third side, okay? And what we used here was the converse of that. But it turns out that this, you can divide this triangle into 4 equal parts by drawing another parallel line here, like that. And then you get a parallelogram here, and you join this parallelogram. And what happens is these 4 triangles are all congruent. All 4, all congruent to each other. So this triangle here, its area is 1/4 the area of the large triangle. So I'm going to repeat that. The area of this piece is, I'm going to rub out these things here. The area of that is 1/4 of the area of the large triangle. So that's one way of looking at it. But the other easier way of looking at it is, I'm going to calculate the area of ECE. Now, just watch. I can avoid using that last result, but it's a useful result to have. Here's the area. Area of EC. I'm not going to put triangle because I need space. Area of CEF. That's what we're looking for. Area of CEF. I'm going to put it over the area of the large triangle. Now remember, the area of the large triangle is 2,400. Oh, okay, we'll put area ABC. We worked it out before. It's 2,400. Now, what I'm going to do is, I just told you that the area of this, over the area of this triangle here is 1/4. So I'm going to squeeze that in, area CEF, and I'm going to put over area of, we'll call this G, the area of CAG. Right? Because I know this ratio is 1/4, but then I have to multiply this by area CAG divided by area ABC. Area CEG, or CAG, divided by area ABC. All right, now it looks as if it's very complicated, but now remember this is A here. I call this A, and I call this A, and I call this 2A. Right? This part here, area of CEF, you can use the sign formula for this. So I got A, I got X, and I got C here. So the area of CEF is actually a half AX sine C, and the area of CAG is half CA, which is 2A, and CG is 2X sine C. Now this part here is actually a quarter. I'm giving you an alternative proof by using the area formula, because sine C is cancel, right? The A's, A and the X both cancel. The halves cancel. And you have 1 over 2 times 2, which is 1 over 4. I told you that this area is 1 over 4 by using another method, using geometry. But you could have used the area formula to get to this to be 1 over 4. So the point is that the first fraction is 1 over 4. I'm going to wipe all these things out. These things all just illustrating that this thing is 1 over 4. So the first fraction is 1 over 4. Now let's have a look at the area CAG. Now if you look at CAG and ABC, now this is CAG and ABC, they both share the same height. And that's not easy to see. CAG, I'm going to just isolate this thing. And see, when you have it, this is a very useful thing to know, that if you join, take any triangle and you join a vertex to a point on the opposite side, then the area of this over the area of that is the same as the area of this over the length of this over the length of that. Now, I'm going to explain why that is so, because what we can do is, if I draw a perpendicular line, like that, this is perpendicular, I call this the height. If you take this, in this diagram here, I got the 2x here. And here I got a y. And this is the area they're looking for, area CAG. There it is. That's the area here, CAG. And the ABC is the whole triangle. So what is this ratio? Now, the area of this part here is half base, that's your base, times the height. They both share the same height, you see. That's what I'm exploiting. This triangle, the height of this triangle is from here to there. That's the height, with this as base. Right? It's not, usually with in obtuse angle triangle, people often don't see this easily. This becomes the base and the height is outside. So half base times height is the area of this triangle, the top triangle. And the area of the large triangle is half 2x plus y, half of 2x plus y, that's a base now, times the height. So this whole thing now becomes, the halves cancel, the h's cancel, and you have 2x over, oops, sorry. So the quarter is there, but, and this part here is what we are simplifying, and that is 2x over 2x plus y. And so I've replaced that, so I'm going to take that out of my thing. And now you need to calculate. You see, I know this denominator, so I need to calculate this thing here. And now the question is, now how is that calculated? And the answer is that I was cheating then. We can calculate x over y, you see. This over this is equal to that over that. So you got x over y. Just one moment. Yes, Law?
Here's your coffee.
Just come and leave it here, please.
No, Nick.
Just one moment, please.
No, so.
Oh, sorry about that. My wife knows it's coffee time, so she brought the coffee. Now let's, what I was saying is that the ratio, this over this, is the same as this over this. These lines are parallel, you see. So they will divide these things the same ratio. So it's actually a theorem. It's called the mean proportion theorem. And now this part here is a side in the small triangle here, where you know this is A. And remember, we call this thing here theta. And this angle here is 90 minus theta. That's 90. But 90 minus theta is this. Okay, so I'm going to leave this to you. Actually, what happens is x over y turns out to be x. Is equal to this, which is a cosine theta. I'm sorry, a sine theta over a cos theta. And the a's cancel, the sine theta over cos theta canceled to give you tan theta. And we saw that tan theta is a half, right? Which means that y is equal to 2x. You cross multiply. And now you can substitute for y here, and you will have a quarter. Numerator is 2x. Y is 2x. 2x plus 2x is 4x. And so the x's cancel and you have 1 over 8. Sorry, somewhere along the line I made a mistake. I'm not sure exactly where it is. Yeah. All right. But whatever, I'm almost there now because I know this part here is 2,400. So therefore you can find the numerator. Area of ACF over 200 is 1 over 8. It actually turns out to be 1 over 12. So I don't know exactly what happens. I'm not going to go back and check. But somewhere along the line, I made a mistake. And once again, you get that this ratio is 1 over 12. So this should have been 200. 200 over 2,400 is 1 over 12. So you come back to area of CEF is 2,200. So this is a very hard problem. As you can see, the two methods that we used were both very challenging. All right, so let's go on to this problem number 24. I told you that this was a very difficult paper. And let's see problem number 225. I hope that is not just as difficult. Don't be put off. Remember, there will be just a handful of people in the whole country who will solve this problem. You want to be in the top 100. So you don't have to be, in the top 3. Only the people in the top 3 will solve this problem. Okay, so don't get too concerned. But it's my responsibility to take you through these difficult problems so that you have an idea as to how to solve even difficult problems. All right? So the next thing we want to do is get to the next problem. Oh, this too is another difficult problem. Let me come back to this if I've got the time. I asked for extra time, but I'm going to come back to this problem because it's a very nice problem. This problem here says, what is the smallest integer larger than this thing? Now, you're not allowed to use the calculator. You can use the calculator and it'll give you the answer immediately. You can work out root 3 and root 2, add them, raise it to the 6th power, and you guys will quickly tell me, there's the answer, right? But if you're not allowed to use a calculator, how do you do this? That is a challenging problem. And it really calls upon all your resources in algebra and everything to say how you could actually solve this problem. It's problem number 25. So it's a tough question. Okay, I'm going to put that on hold because after this, the problems are a little bit easier and I don't want to put you off. I don't know how many people are still sticking around. They probably went away in disgust. Okay, so let's go to the nice problems now. Let me see how many people are here. We still have 72 people. That's good. You guys have got tenacity and guts to go through this.
So there are 72 accounts still on the Zoom. It's possible that some have turned away from the computer.
Some of them might have gone away. No, I'm sorry. What is that you said? I didn't see who it was.
I made the joke so that some people's accounts may still be signed into the Zoom lesson, but they may have left the computer.
Oh, okay. Okay, Kristen, thank you for that. Now I'm just going to take a little break here to have my coffee. That's a nice cup of coffee. Now let's go on to solve this next problem. We're going to much easier terrain now. Let's share the screen. Right. Well, I'm saying much easier terrain, but it's still quite challenging. If you look at this problem here, you got two opposite corners of an 8 by 8 grid are removed. So 62 squares are left. You have 31 1 by 2 dominoes. There is a little picture there that shows you what a 1 by 2 domino is, right? In case you don't know what dominoes are. So this is a little 1 by 2 rectangle. And the idea is you got 31 of them. You got 62 squares in this thing. The question is, can you place these 31 dominoes so it fills up the entire grid? Right? Well, you can draw it and you can start filling up. You can fill up maybe these two like that, and maybe fill up those two, and then fill another two, and so on, and try to fill the whole lot. And the question is, can you place? Now, very often when you have a question like that, the answer is no. And so that immediately tells you it can't be done. And in a situation like that, the best strategy is what you call the proof by contradiction. Very, very powerful method of solving problems. What it means is that you assume the opposite of what you want to prove. Now, I'm going to think, I'm going to say it can't be done because this question is like that. So I'm going to assume the opposite of that and say, if suppose it can be done. Now that's your starting point. In a logical argument, now, then you use this fact to come to something which is impossible. And then the moment you come to something which is impossible, you say, hey, what happened? All my steps were correct, but it's impossible. I've just proven that 8 is equal to 10, right? Then you say, it means the very first statement that we made, that was false. Otherwise, we wouldn't have come to something which is impossible. So if this is false, then it means, therefore, it cannot be done. See? So that's how you will prove this. It's a very, very clever way of proof by contradiction. I prove a lot of things by contradiction. Okay, now suppose it can be done. So what happens? You fill this whole thing up. Now here is the trick. 8 by 8 was not chosen deliberately. The idea is 8 by 8 is actually a very familiar figure for a grid like this. It's the same size as a chessboard. So why don't you make it into a chessboard? But to make it into a chessboard, you have to color the squares. Okay, so I'm going to get to the next page. I'm not going to draw this whole chessboard. Oh, I'm supposed to stop sharing. New share. Right, there we are. Okay. Let me just clear the screen. Okay, now we draw the chessboard. The chessboard is now colored. You got black and white square. And we said it can be done. You've got 31 dominoes. And I'm going to place the dominoes. When you place the dominoes, note that each domino will cover one white square and one black square, exactly. Right? No matter how you place them, they will color one white and one black. So when you place it, you see, you have placed them. Now you said I'll cover the whole thing up because it can be done. So what happens is that I've now placed 31 dominoes. Therefore, we have covered 31 black and 31 white because each domino covered one black and one white. But watch here, I've just covered 31 black. But these two corners were removed. And if you look at them, you'll see they got the same color, right? Which means the two blacks were removed. Two blacks were removed. But we had 32 blacks originally. So we only got 30 blacks in this new configuration. In this picture here, without the corners, we got only 30 blacks. And we just said we covered 31 blacks. That is impossible, right? Therefore, we have a contradiction, because how can you cover 30 blacks with 31 dominoes? It's impossible, right? So therefore, we have a contradiction, and therefore the answer is we conclude that it is impossible to place the dominoes as required. Okay, so that's the first of the new problems. Let's get on to the next one. Okay, now you've got a similar kind of a thing. But this time you got a 10 by 10 chessboard. And again, you've got tiles. And once again, the question is, can you use these tiles like this one? This time you don't have a 2 by 1 domino. You got something else. You can call this a domino also. But this is the funny shape of this. Now, a 10 by 10 chessboard has got 100 such squares. I haven't drawn it. And this one has got 4. So you may postulate that, okay, I've got 25 of these. If I've got 25 such tiles, I might be able to cover it. And once again, now you can go and try to cover it, and you will see that you are failing each time. But that doesn't mean to say that it cannot be done, because there are billions of ways of covering it. And you can just try another 20 or 30, and if it fails, you still don't know whether the other billions which you didn't try, some of them will work. So this is a very, very difficult kind of problem if you try to do it directly. So now you have to use some method here. And again, we do it exactly the same way as we did it, as we saw before. This time you have a chessboard. It's not really a chessboard, but you color it. It's a 10 by 10 thing. So there's no chessboard which is 10 by 10. You colored it. Yes, but so you color this 10 by 10, and now you look at it. Now, if you color any particular grid, and you will have, it's like this, right? When you cover this thing up, it might be like this. It's either covering 1 black and 3 whites, as you can see, or it'll cover 1 white, if you put it this way, and 3 blacks, right? It'll always be like that. You cannot cover 2 whites and 2 blacks. It's impossible, right? Because these are the way the chessboard is colored. It's impossible to do that. So you can have either 1 white, and so we will suppose. So by the way, we assume, just like before, we assume it can be done. And I'm going to prove again, as before, that it's impossible to do it. So it's the same start, and then we say we've got so many. These are 2 types now. So we'll call type 1 where these dominoes, we'll call them dominoes, where they cover 1 white square. And the other type 2, will cover 1 black square. So there are 2 types of dominoes. those which cover one white and those which cover one black. I don't know how many of these. Suppose we are saying we are covering the whole lot. So suppose we have M of type 1 and N of type 2. So we've covered the whole 10 by 10 grid. There are 25 of them, and M of them of one type, N of another type. So you got M plus N equal 25. This is the total number of such dominoes is 25, and some of them cover one and the others cover one white and the others cover one black. But whatever it is, you've got M plus N equal 25. Now we've got M is the one white one. So the M, how many whites do these M tiles cover? Well, each one covers exactly one white in the M of them. So these tiles here, they cover M white squares, but each one of them covers 3 black squares. So they will cover 3M black squares. That's the type 1. The type 1, I've got, what I'm saying is white and black. Let's just draw a grid like this. This is type 1. You got type 2. Now the type 1, the M of them, so they will cover M whites and 3 M blacks, while the type 2 will cover 3 M whites and M blacks. Now N. These are type 2. So you got N's there, right? The N of them in type 2. So they will cover M blacks. So now, what do we have? The total number of white squares covered in this 10 by 10 is M plus 3N. The total number of whites down here. And the total number of black squares covered is 3M plus N. Right? By these two types of tiles. Oh, he's calling it tiles, is it? Not dominoes. But the point is that this is the number of black squares covered and this number of white squares covered. And in coloring this just 10 by 10 with black and white, you will have 50 blacks and 50 whites. It's 10 by 10, right? So you'll have half of them will be black and half of them white. In other words, the number of whites covered, these are equal. Because this is the number of whites covered, we're covering the entire thing. And this two, and they're both equal to 50, but they're equal. Now, when you got the single equation with two unknowns, bring all the m's to one side. If you put the m's on this side, 3m minus m, and the n's on this side, 3n minus n, you have 2n equals 2m, so you have m equals n. So if you assume that it can be done, it means that the number of tiles which cover the white is the same as the number of tiles which cover the one black square, right? But m is equal to n. If you go back to this equation here, m is equal to n, so let's just replace the n by m, and you have 2m equal 25. Oh, but wait a minute. That's not possible because m is a number, a natural number. It's a number of tiles which cover one white square. You can't have, this is a fraction now, m is equal to 12 and a half. You can't say 12 and a half tiles. We know m is a whole number. So there is your contradiction. Right? Somewhere you come to an impossibility. You can't have, 25 is an odd number. and this is an even number. So we are saying an even number equals an odd number, which is ridiculous. So that is how we get to the contradiction. Therefore, the thing is it cannot be done. So just to go over this again, it's a matter of counting and using your information and bringing in symbols which will help you to solve the problem. And so what we did was, we said, assume it can be done. And then we did use the same strategy as before. We colored it. And then we see these things color, they cover white squares and black squares. Then we counted how many white squares do they cover, how many black squares they cover. We'd like to make a count of that, because we know if it's completely covered, we have an equation that the number of white squares covered is equal to the number of black squares covered. So there's somewhere you have an equation. So we count the number of white squares covered, we count the number of black squares covered, we make them equal, and we see that that gives you, but to count them, I have to know how many of these tiles, the one white tiles are, and how many of the one black tiles are. We give names to them, we don't know what they are. We only know that they add up to 25, and then we get some equation and we get a contradiction. So that is the long and the short of the story. It's a logical problem, and you assume the opposite. All right, so let me now get on to the next question. Okay, so you have another thing here. Okay, we finished with this. All right, I'm going to. So this is a game. Maybe we can play. Okay, the game of tactic. Not bad. In the end, you have to develop the tactic, which will give you the answer. There's also another game called tic-tac-toe, which I'm sure all of you play or have played. So this is a new game. The game of tactic is played between two people. Right. Firstly, during a turn, a player selects a row or a column and at least one cross. So what happens is, it's got some kind of a configuration like this, a 4 square, and you got a board which has got a cross like this, right? You can put crosses anywhere, but this particular game has got this situation here. And what does the player do? He selects a row. You have to understand this. He selects a row or a column and removes at least one cross or any number of adjacent crosses from that row or column. So let's understand the rules. He selects a row or a column. All right, let me oh, I chose the wrong one. Okay. Sorry, just one moment, please. Right. This is a nice little arrow here. Suppose I choose this row here. Right? He selects a row and a column, so we just selected it. He removes at least one cross, so you can remove at least one. So he removes here, either removes one or two, or any number of adjacent crosses. Now here, there are no two crosses which are adjacent, they're isolated. So he can, if he selects this row, he can remove that cross, or he can remove that cross. And likewise, if you selected this one, you can remove that cross. If you selected this, you can remove that cross. But if you selected the first column, he can remove that one cross only. But here, if you select this column here, he can remove one, like this one here, or you can remove that, or you can remove that, or you can remove any two adjacent. So we can remove these two, or you can remove these two, or you can remove all three because they're all adjacent. As long as they're next to each other, you can remove any number, but they must be adjacent to each other, right? So now that's the rule. The second thing, this is the player who removes the last cross from the board wins. So guys, over to you. All right, so I'll give you a chance to play first. Who wants to play first? You must play first so that I will be left with only one cross, and then I'm forced to remove that. And oh, wait a minute, no. You must have one cross. The player who removes the last cross wins. So you must have the last cross so that you will win. Right, who wants to play? Helen? Right, what do you do, Helen?
Okay, I would remove the cross in 3C.
Third column, okay. 3C is third column.
Third row.
Yeah.
Yeah.
Oh, the single column in the third row, eh? So you'll remove this thing here.
Yes, and I would choose the
Right, okay. Now you have done that, right?
horizontal row.
So in other words, you've taken this out. Okay, let me just
Yes.
move it around.
With the
It's my turn now, right? It's my turn. Two players play, right? You remove this. So I'm going to play, and I'm going to remove this. It's your turn.
Yeah, got that one wrong. So
Right, you got that wrong. You understand? It's your turn, but I will finish it off. Okay. So hopefully you all understand the way this thing works. Let's play again. All right, who wants to play with me? Come on, next one. Helen offered the first time. Okay, three participants. I don't know who it is.
Sir, I'm saying that I would. Can I answer?
Yeah, okay.
Okay, I'm saying that I would remove 3B and 3C.
So you'll remove 3B
and 3C.
No. There's use either row or column. So you'll say one row is the first row, 2R, second row, 3R. So what are you removing?
Okay.
The column.
Oh, at the column number 3 and row number 2 and number 3.
So you're removing this one here and that one.
Okay. Yes, I'll remove those two.
Okay, so you remove those two. Right, okay.
Yes.
So it's now my turn. This is removed. Let me just take this off. So you are allowed to remove that because they're adjacent. Okay, now it's my turn. I've lost because no matter what I do, you will be the last one to play. Okay?
Yes, sir.
All right, so
yes, sir.
Well done. So now he played with me and he won. So what is the strategy?
Somebody
else can answer the strategy.
Okay, it's fine.
The strategy is to remove two adjacent column crosses from the third column, right? Okay, so actually there was no question. So you already got the answer. Okay, so that's finished now. But they say describe all possible first moves. Right? So what are all the possible, how many possible first moves are there which will guarantee a win?
I think 2.
My friend took these two out. That was a possible first move. Is there any other possible first move?
Yes, Prof.
Which one?
If you remove third column,
Yeah,
the first two crosses.
right. So you could have removed. Are there any other possibilities? Those are the only ones I think. Yeah? All right. So there are two. The answer to the first one is 2. Okay, now let's get on to the second problem. Got the same rules. Find a winning move for this configuration and explain why it works. All right, now you can see this is considerably more difficult. Right? There are so many possibilities. I can remove all these here. I can remove those two. I can remove those two, or I can remove any one of the whole lot. So lots of possibilities, and we're not sure how it'll go, because the next player will have to play, and then you will play, and then he will play. So you don't know what kind of move he will make, or he or she will make. So you have to figure out a winning move and explain why it works. So there's a strategy. And I want to tell you what the strategy is, because if you don't know it, then it will take you a long time before you eventually find the strategy. And the strategy is used many times. So if ever you have a question like this, you'll be able to solve it. We've got other problems like this as well. Okay, so the strategy is actually the following. The strategy is you create a situation which is symmetrical. I'll repeat that. Create a situation which is symmetrical, and you have, by that I mean, you have two disjoint groups. By disjoint I mean they are nicely separated, right? But they must be exactly the same configuration. Now, anybody can tell me how you do that? What must I remove so that you have two disjoint groups which have the same pattern? What must I do?
Remove the cross in the bottom row and third column.
Right. You remove, in the bottom row, you remove the cross in the third column. Right. So you remove this one here. Right. Now, I suggest to you that I must win. I did this. It's your turn. Suppose now you say, well, I'll knock these two out. Right? I will do exactly the same on the other side. Now it's your turn. Got it? Whatever you do on one, I will do on the other. Because it's symmetrical, you see. So I can't do that. You can take out this cross, for instance, then I'll take out that cross. See? If you take out this corner cross, I will take out the corner cross. I will leave the same pattern for you. I just change the pattern, but I will leave exactly the same pattern, right? And so each time you do something, I will have a move which is exactly the same as yours. So, so in the end, you'll have to leave two for me, and then And then I'll leave you too. You see, I'll always leave. Then you have to take the last one, second last one, and I will take the last one. So that is the way to do it. So understand the strategy. So let's get on to the next one. Okay, now the next one is okay, that's all. I'm not going to play any other those kinds of games, tiling games. If you go to my book, go to tiling, Tiling, and you will see some other games like this where you can cut your teeth into that and try to solve those problems. Okay, you know the strategy now. So let's get on to the next question. So this is, I'm going to explain this thing here because it'll take a long time. I'm going to explain to tell you what's going on here. Now in this problem, you've got somebody who is doing some kind of research in a town. And this diagram here, you see this diagram here, these are all buildings. These are all buildings, each one of them. They got a number associated with it. I'll tell you what that number means now. These are buildings. But each building has got a number of stories. So this building here, it's a normal building. It's a 1-story building. But this one here is a 3-story building. It's a 4-story building. And this is a 2-story building, right? So like that now you got each building is described by the number of stories it's got, number of floors if you like, right? So this is the tallest. If you take this one here, this is the tallest in this row. It's also the tallest in that because 4 is the largest number that you can get. Okay. Now, in addition to these, you've got other numbers outside here. You got these, right? Now, what this represents, what this says is the following. This guy, this researcher, he stands here and he looks at this line and he jots down how many buildings can he see, right? Now, if you look at this, you can see this one here. This is taller than that one, so you can see this as well. This is taller than that one, you can see that. But you can't see this one here because this is dwarfed by the other two. So you can see 3 buildings, and that's why we put 3 here. See? How many can you see? All right, let's take another one. If you take this number here now, this number on the edge here, it says you can see only 1 building. And if you look along that line there, that column, you can see 4, but that's the tallest building, so you can't see the other 3. So you can see only 1. So it jots down 1 here. Likewise, here you can see only 3, he puts down 2. Here you can see only 2, and he puts down 3. See? And here, for instance, what can he see? He sees 3, and he sees 4 as well. But he can't see these 2. So he puts down 2. So it's an interesting problem. Jonathan, he goes all around this place and he writes down only these figures. And he does that. This is just an example. But what he does is actually he goes to a place where there are 5 by 5 buildings. He goes to something which is a bigger complex and he does exactly the same thing. And what he does is he goes to this thing here and he's got a 5 by 5 grid, as you can see. And then he writes down the numbers of buildings that he can see at along each row and each column. You can see all these numbers here, right? And our job is to populate this grid. In other words, how many floors are there on each of these grids? On each of these. All right, it looks like a very difficult problem, but You can see there are 5. Oh, by the way, also each row has got, like in the previous case, I didn't say this. The question should have said it. See, you got one building which is 1 story, another one which is 2 stories, another 3 which is 4. 1, 2, 3, 4. 1, 2, 3, 4 is repeated in all the rows and the columns. So that's an important fact, right? No number is repeated anywhere. Okay, so that's going to be very useful. Now the place to start here will be where you can see only 1. What's the conclusion when he sees only 1? Right? You can answer.
The tallest building must be there.
Yeah. Let me just something. I seem to have knocked out all my participants. I can't see who's talking, which is normally a useful thing to do. Just one moment, please. Okay, I'm back here, but it seems that I still don't know who's talking. Okay, that's tough. Now, where there's a 1, if he sees only 1, what's the conclusion? Somebody give me an answer.
That it must be the tallest building.
Yeah, the tallest building will
At the
be
beginning of
right at the front. Right, okay, that's useful. Let me. Sorry, even after all these usage, I still struggle to. Okay, so the 1 here. So the tallest building must have been here. You can't see anything else, right? And the same thing happened on this side. Okay, there's a 1 here also. So the tallest building must have been here. And there's a 1 here as well. So the tallest building must have been right in front because it blocks everything else out. Okay. So the 1 is a useful number. Another very useful number is 5. And there is only 1 5 here. Why is 5 a useful number?
That's the building that will be used to see 5 buildings.
Right, which means that all the numbers are in increasing order, isn't it? You can't have a taller building in front of a shorter building. You start from here now. The shortest one will be here. The 2-story one will be here. That's the only way you will have 5 here, right? If you had anything mixed up, you had a 4 and 3, then something is going to be dwarfed. Nothing is dwarfed. That's the important thing, right? Okay, so like this now, logically, you can argue it's not an easy problem. Now, you might think, for instance, now that the okay, now look, I've got a 5 here, I've got a 5 here, and I've got a 5. There's something like a, what's the name of the game you play? I don't play it. Sudoku. Sudoku. I don't play it. I find it very hard.
Prof, just one question.
Yes, Ellen.
Just one question. Surely where you can only see 1 building, it doesn't necessarily have to be 5. It can be 4 and still be the tallest building.
No, I told you every row has got 1, 2, 3, 4, 5.
Okay, so no doubles.
No
in
doubles.
any row.
No doubles.
Okay.
Every row has got all 5. Right. Okay, thanks for that question, Helen. Now, here's another observation. You already got a 5 here, you got a 5 here, and you got a 5 here. So it means that this thing here is either, there's a 5. The 5 in this row can be here or there, in this column, right? It can't be here, can't be here, can't be there. Okay, let's just assume it's here. So suppose 5 there. Now, anybody can tell me what's the next thing I can do? I can put the fourth 5, right? Isn't it? I've got 4 5s here already. So this has to be a 5. Okay? Are you happy with that? Okay, so I've eliminated my 5s. The next thing now to do is to put in now you can see 3 in this thing here. You can say 3. So this could be 4, 3 and 4. Or actually you can have 3 and 4, 2 and 4, 1 and 4. You can see 3 of them. So that doesn't have too much. You can see, all right, you can see 2 here. So this thing here will have to be 5 is one of them. This has to be 1, 2, or 3 because you've already got. All right. And you can see 3 here. All right, now, yeah, this, the question is, where do I go next here? Oh, you can see 4 on this one here. Ah, that's nice. Here you can see 4. That one there. And there's a 1 sitting behind here, right? So that means the only way you can see 4 is that the 5 is here and nothing is dwarfed. Right, that's a good start now. Okay. So like this now, you can go on and fill up the whole thing. Okay, I think we've got a fairly good start here, and you can logically work this thing out. I will tell you what the answer is, right? You can put the thing away, put the answer, and then you develop it all over again. The answer is 25413, 31254, 43521, and 54132. This is the answer. You can write it down if you wish. I will send it to you, but maybe you can try it as soon as we leave. Okay, let's get to the next problem, because we're already at 11 o'clock, and I did ask you permission to go on. Let's get to the next problem. Okay. Now this problem here is a problem which is similar to the one that we had earlier on. So we got 3 such problems. Okay, that you can try now. I've already done 2. So this is an example of a third problem with a so-called tiling problem. And you can try this. Let me do this one here. Now these problems are taken from the book. P83 means the problem number 83 in the book. If you open the book and if you type P83, Control F, P83, you'll go straight to this problem. And if you click it again, you'll go straight to the solution. See? So you can try it and then you can check to see whether your solution is right. But we are going to discuss this thing here now. Now, how do we solve this problem? This problem, it says the following. You got this thing here represents a block of flats. In other words, there are people living in all these white rooms here. And the middle one is a stairway. Right. Now, and it's high up because these people have views. They can see in different directions. They have good views. So you have people living in each of these. These are all single flats. And there are a number of people who live in each one of them. And it says here that there are windows on all the buildings. All the sides you got windows. So the people can look to the north, or they can look to the south, or any direction you prefer. But actually these guys, they can only look to the north. So these people, they can see all these. Now these guys can see all the west directions. And these guys here can see all the east directions. I don't know what the south is doing here. It's wrong. Take it out. And these people can see the southerly direction. Okay. Twice, there are windows on all sides, so which afford good views. Twice as many people have a southward view as there are people who can look eastward. Now, we don't know how many people can look eastward because we don't know how many people there are in each of these rooms, but these guys are the people who look eastward. So let's say that the symbol E represents the number of people altogether in that lot. So that's a nice symbol to use. When I use capital E, it means the total number of people here. Capital N is the total number of people here. Capital W is the total number of people in all these 3 rooms. And capital S is the total number here. Now we've got an equation. Twice as many people have a southward view. So if you look at the south, right? Whoever the south, there are twice as many people who have this view. Twice as many people who have this southward view who can look eastward. So the number of people who are looking eastward is 2 times S. There are more people who can look eastward than who can look southward. Now, likewise, those with the westward view number only 1/3 of those who look south. So the westward view is 1/3 those who look south. Well, the few who have a northward view number only half of those who can look east. So those who look north is a half of those who look east. Altogether, 20 people live in the 8 flats. So if you add up all the 8 numbers, the 8 flats, right, you'll get 20. And you have all these pieces of information. The question is, how many occupy each flat, given that no flat is vacant? So the problem is to actually get the numbers in each one of them with the information that we have. All right. So let's just rewrite some of them.
Sir, shouldn't E equal half S, since south is twice as much as E?
Which one are you looking at? The first one.
Twice as many people have a southward view as there are
Oh.
people that look eastward.
Oh, yeah. So the south is more, eh? Sorry. Thank you for that. Is that right? Are you happy with that?
Yes, sir.
Okay, thanks for that. That's very important. Okay, so you've got, so the, oh gosh. I just want to check something out. Sorry. Right. Now, let's just get rid of these fractions. Yeah, I'm going to rewrite this. I don't want to go into a new page. W equals 1/3 S is the same as saying that S is equal to 3W. I'm going to get rid of the fractions. Sometimes this thing messes around. So this is S is 3W. And likewise, N E is equal to 2N. Get rid of those fractions. And now S is equal to 2E. So S is equal to 4N. Or let's write these equations down. You've got S is equal to 2E. And let's put them together. You get 3W. And 2E is 4N. So I'm writing all these equations and putting them together. And I've got you got quite a few equations here now. Now comes the difficult part. The part is that, not difficult, the observation, that these numbers N, E, W, and S are all whole numbers because you're talking about number of people. So what does this mean? It means that S, if I take S, it's 3 times the whole number. So S is a multiple of 3, right? Agreed?
Yes, Prof.
And S is also a multiple of 4. Because S is equal to 4N. So to get a number which is a multiple of 4N multiple of N, it means that the only number which will be that is 12. So S has to be 12. Which number is a multiple of 4 and multiple of N? You see, there are 20 people altogether, right? So the only multiple of 4 and 3, the multiple of 4 and 3 have to be multiples of 12. Less than 20 is 12 itself. So this is 12. Right, now you got S is 12. So if S is 12, N must be 3. For N is 12, you see. So N is 3. But there are only 3 rooms, And it's said here that no flat is vacant. So none of these flats have got 0 people. And when you add up all these people, you're going to get a 3. There's only one way to do it. See, they're all logical problems. So you have to have that each one of them is occupied and they add up to 3. So there's only one way of doing that. Okay, so we've got n. Now remember S is 12. So W is 4. W is equal to 4. So the number of people who look this way here is 4. You already got 1 here. So you could have different ways of adding up to 4. So these two add up to 3. And likewise, if you look at E, S is 12, so E is equal to 6. So all these things add up to 6. Oh, I'm sorry. When I say S is 12, I'm sorry, man. It means that the total, the 12 is not here. The total number here, when you add up all these numbers, you're going to get 12.
Prof, I started with West because it's the next smallest number to work with.
Which one?
With West.
Yeah.
Because for the flats left, one has got 1 occupant and the other has 2. But South has got the most people
Yeah.
facing there. So
Yeah.
then I made it 1 and then 2 at the bottom. And then from there, I worked it out.
So you made this 1 and 2. Okay. You could have made it 2 and 1. You could have made it 1 and 3 as well. So you tried various possibilities. And then eventually you needed to get 20 altogether. But another useful way is you got 12 altogether here, and you got 3 here. It's 15. So these two will have to add up to 5. See? They both have to add up to 5. So you can't have So they have to add up to 5. So if this is 1, this will have to be 4. And you got 1, 4, and you'll have to have 2 here. All right, okay, you can try out various things here, but there is a logical way of determining this middle number here. Let me just write this thing down. I'll show you. I hope I remember what it was. I can actually prove that the middle number at the bottom is 9. What's the reason for that? Anybody can see it. We know the whole thing adds up to 12. You can prove that the middle number is 9. These add up to 6 here. These add up to 4. These add up to 12. I've forgotten how it goes, but let's just do it. I'll go and look at my solution to see how I concluded the middle number is 9. See, I actually did some, put some symbols for these things here. So we do use some mathematics to get the middle number is 9. All right, so I said that Akim to S is equal to 12. right? And we got these, which we came to. But now we say that east plus west is 10. Oh, I see. So we say that these two add up to 10. Ah, right. You see, this is 4 here, right? And this is 6, right? Yeah. So 4 plus 6 is 10. So these two numbers must add up to 10. Right? This is 4. These three add up to 4. These three add to 6. So altogether, these numbers add up to 10. The remaining two will add up to 10. Altogether, you got 20. One of them is 1. So this has to be 9. So once you got the middle number is 9, then after that, it's just a matter of technique to get the rest of it out. Actually, there are two answers to this problem. There are two possible ways in which you can fill the houses. So you can do it. We've done most of it now. So you can try the rest of it. All right, so let's get on to the next problem. So next problem is another very challenging problem. A very interesting problem also. Let's see what this problem says first. A camel sits next to a pile of 3,600 bananas at the edge of a desert. So it is at the edge of a desert. He has to get as many bananas as possible across the desert. He's going to travel across the desert. And the desert is 1,000 kilometers wide. So we'll just keep that in mind. He's got 3,600 bananas here. And he wants to go across the desert and he wants to take as many as possible, right, across the desert. The problem is that he can carry only 1,200 bananas at a time. He carries 1,200. Maybe you can say he carries 1,200. Yeah, but what else do you say? To survive, he has to eat 1 banana for each kilometer he travels. So for each kilometer, he eats 1 banana. It's interesting. I didn't know that camels eat bananas. Camels, that proves that there was some connection between camels and monkeys in the Darwinian chain. Monkeys in my garden keep eating all my bananas and we have to cover them up. Now you've got each kilometer he travels, he eats 1 banana. Okay, so what we're going to do now is we're going to make this camel, fill him up, 1,200, make him go up to a certain point. We don't know where. Right? But for each kilometer he travels, he eats 1 banana. So let's just call this first distance where he stops at, let's call it X kilometers. Now let's see what happens here. Suppose he travels X kilometers and maybe there's an island or whatever it is, what do you call those things in deserts where you have palm trees or whatever? Okay, so he takes us 1,200, but what happens is he doesn't take all 1,200 here because when he comes here, he has got 1,200 minus X because he's eaten X of those bananas. For each kilometer, he's eaten one banana. So he's eaten X bananas and he lands up with 1,200 here. So now what does he do? He doesn't take any bananas back, but he goes back now to collect the remaining part. We had 2,400 left here because he took out 1,000. But actually, yeah, he carried 1,200 away, so he had 2,400 left. And he's taken the bananas from those which he was carrying. Right, now he goes back. But to go back here, he has to have X bananas in stock. So he takes away X from here. So he removes X bananas from here, which reduces the number of bananas here to 1,200 minus 2X, taking away X. Uses these X bananas to go up here. By the time he comes here, he's finished his bananas, but he's now ready to carry the next. The question is, in the end, what is the maximum number? So you have to carry as many as possible each time. That's why you must carry 1,200 bananas on each journey. So that way you will optimize. So again, he takes 1,200 bananas, goes up here, and from those 1,200 eats another X. He lands up with 1,200 minus X bananas here. So together with these, right, there are 3,600 minus 3X bananas here now, because he's taken these and added it to whatever was left there. Right, now he's still got 1,200 bananas here. He goes back, he takes X away from here, from this lot, goes up there, right? He's finished his X bananas, and from those 1,200 bananas, he now eats X. So he's got, it's 2,400, I'm sorry, 12 plus 12 is not 36. Don't know what 12 plus 12 is. Okay, and then to this lot here now, he adds another 1,200 minus X. So when you look at it, he eventually has 3,600 minus 5X. Now, so I'm just going to put that down here. He's got 3,600 minus 5X. We don't know what X is, but we would like to know what the total amount here is so that he can take as many bananas as possible to the other end, right? So he wants to have as many bananas as possible at this. He can't have 3,600, obviously. He's eaten some of that, but he would like to have maybe 2,400 here. He'd like to have 2,400 because he wants to carry 1,200 each time. So it'll be nice to have a multiple of 1,200, yeah? So he's got this. So he'd like to have this. So these two, whatever he carried over, you want it to be equal to 2,400. And you can solve for X, in this case here. And when you work this thing out, you get 5X is equal to 1,200. So X is 240. He travels 240 kilometers. And when he travels 240 kilometers, he lands up with 2,400 bananas at this lot. So I'm going to remove all the other stuff which are used for calculating. Right? I just want to put what we got now eventually. So he's got 2,400 bananas here. He's got 2,400 bananas. He's traveled 240 kilometers. And now he still needs to move on. Now he needs to carry these 2,400 along with him. Okay. He does exactly the same thing now. This time, let's say he stops at Y. Carries 1,200 bananas from here. At Y, this is Y kilometers. At Y, takes away another y from here because he wants to go back. Right? Finishes those y bananas. Right? But he's only got 1,200 left here. So he carries all that stuff with him and he eats y of that. So you got 1,200 minus y plus 1,200 minus 2y. So he's come up to this point. And once again, he'd like to have, he's going to have less than 2,400 here, but he'd like this number here to be 1,200. So that he has as many bananas as possible on this last leg. So now you can calculate y, and you see that y is equal to 400. Y is equal to 400. And at that stage, he's got 1,200 left here, so you can remove all these other things. Remove all these calculations. And now he's got 1,200 left here. Now he just keeps going up to 1,200. And yeah, how many kilometers has he got left? He's got 240. He's traveled 640 already. So he's got 360 kilometers to go. So now he doesn't have a problem because he carries all 360. He carries all this with him to the end of the journey. But he eats 360 along the way. So in the end, he lands up with 840 bananas at the end. The last leg is got 360 kilometers to travel. He carries the last 1,200 that he's got. So in each case, he's carrying 1,200. So that allows you to carry the maximum number of bananas, right? And that is the problem, is to observe that all the time, and eventually you get to this. Okay, there was just one question. He might have decided to leave 1,200 here rather than 2,400. When you try that method, you will see you're going to land up with less bananas at the end. So this is a better option. Okay, so I think that's the answer to the problem. I hope I can do all my calculations correctly. I usually mess up with the calculations. Hey, 680. Let's see, we would have transported 1,200, 640, that's fine. The camel eats 360 bananas along the way over the last trip. So 840 bananas reach the, oh, I see. Oh no, my 840 is correct. This is best possible. And in the other case, I calculated that he would have calculated at 680, so I wasn't wrong. All right, so that's the problem, the banana problem. Well, the nice problem, you see, the mathematics is not much. All these are long linear equations, solving for x, very simple equations, but there's a lot of thinking involved. And that's what mathematics is all about. Problem solving, right? Problem solving. How do you solve problems? It's not solving, finding, solving trinomial and factorizing it. Right? Those are just techniques. Those are techniques which you would use to solve real world problems. And here we have got real world problems. You've got a story about a camel and so on. But you'll notice that the mathematics that you use is not much, but the thinking is involved. See? And that is what we are trying to cultivate in this, in Olympiads, to refine your thinking so that you argue it out and you see what is best possible and so on. You don't just make mundane calculations without any thought. Every time you say, what must I do? What must I do? What is the best method to solve it? You are solving problems at every stage. That is the point. See? So again, now you got this situation here. You got 68 coins, no two of which have the same weight. You also have a beam balance, which can tell which of two weights is the greater. Now, what is a beam balance? A beam balance is something like this. Something pivoting around here, and you put a weight here, and you put a weight here, and one of them goes down, and the other goes up. So you'll know that this is heavier. So that's all. It doesn't tell you how many grams it is or whatever. It just tells you, if you put two things on both sides, it'll tell you which part is heavier. That's all. Right. Now explain how you would be able to find the lightest and the heaviest coins in these 68 coins in 100 weighings or less. So you're going to make 100 weighings or less, and you want to find out which is the lightest and which is the heaviest amongst these coins. But no two of them have the same weight. Now that's very useful. So if I match any two of them, one must go down and the other will go up, because no two of them have the same weight. That's useful. So every weighing, you can make a conclusion. So one goes down and one goes up. Right? If you weigh them one at a time. All right, so what do we do? Now, the way we argue this thing out is, I have to weigh every coin, firstly. I can't isolate any coin. If I isolate any coin, it may be the heaviest, it may be the lightest. Right? So I have to weigh every coin. So naturally, the first thing you would do, and then you have to weigh them against each other. So you'll know, you can make a conclusion. So you could put 34 coins and 34 coins on one side. I don't know. You could try that. But then you see one will go up and one will go down, and they're all mixed up now. All different weights. So obviously, if you put 34 on one side, put 34 on the other side, one will go down, one will go up, and you can make no conclusion. So you have to weigh them one at a time. So what I'm going to do is I'm going to put two lines, 34, 34, 34 in one line, and I'm going to put 34 in another line. And I'm going to weigh them against each other. So I weigh these two. When I put these two on the beam balance, one goes down, the other goes up. The one that goes down is the heavier one. So I'll put the heavier one, the one that goes down, I'll put it here. Now I'll do the same thing here. Put the heavier one here. I'll just isolate it and isolate the lighter one here. Let's put some other color for the lighter ones. I'll put the lighter one. So each time I weigh it, I got a conclusion. And you have the last one is right. So you got we've just used up 34 weighings. 34 used up because we had 34 coins, 68 coins originally. So this took up 34 weighings. I still got quite a lot left because I got 100 weighings. Okay, so what do I do now? Well, quite clearly the heaviest one that I'm looking for will be amongst these. Right? But which of these is the heaviest? All right, so how do you go around doing that? Well, we have to weigh them against each other. Suppose I weigh the first one against this. Suppose I weigh these two. I'm now looking for the heaviest one. When I weigh those two, I can discard the one which is lighter, right? That gives me one weighing. Now, then I take the one which is heavier now. This is a candidate now for the heaviest. Now I match it against the next one. And I discard the lighter one. So I'm holding the heaviest of the three now. And you keep doing this, right? You can see I've got the first weighing here, the second weighing here. And the last weighing will be the 33rd weighing. Right? First two, last one will be the 33rd. So in 33 ways, you can find the heaviest. And likewise, in 33 ways, this time you will weigh them against each other and you'll discard the heavier one because you're looking for the lightest. The lightest is here. And again, in 33 ways, right, you discard the heavier one in ways like this. So you retain the lighter, and each time you get each one is lighter than the others, so you can get the lightest. So if you add up this, you get exactly 100. So they say 100 weighings or less, so you just make it using this method. Right? I don't know whether there's any other method which will give you something which is lighter. So guys, this is the last problem that we have in this. And there is only one problem which I said I left out, and that was, which one? I said that'll take a long time. I'm not sure which one that was. So you got one more problem to go. Okay, I see a number of people have moved on. So we got the last 35 people who are brave with the weather. They are staying on for, it's not easy to stay for almost 3 hours at a stretch. But I'm in the same situation. I've been talking for 3 hours, but then I had my cup of coffee somewhere along the line, which is, a coffee to me is like a banana to a camel. Okay, so what we do now, we go on. Not too sure which one. Oh, let's, I said one will take a long time. That I did. Ah, this one, yeah. Okay, that's a very interesting problem. And those people who have remained behind here would hopefully, I hope you appreciate this problem. You see, I'm going to go to a whiteboard because the problem itself is easy. I don't need this question. Let's clear all the drawings here. All right, so you want to work out, can you all see the board?
Yes, Prof.
All right, I want to work this out. I want to know the smallest integer which is larger than this. Now, we can try it, but the problem is that you don't know what this value is, the square root of 2 and square root of 3. You don't know what they are. Right? And when you come to any particular answer, you still don't know how close you are to the answer because these are irrational numbers. So let's try something. For instance, now I can square that one. I can square that one and then it'll become the cube of whatever answer I get. When I square this, I get 3. If you square square root of 3 times 2 times root 3 times root 2, a plus b all squared is a squared plus 2ab. And when you find the square root of 2 and you square it, you get 2. Okay, you can simplify this. And this is 5. 3 plus 2 is 5. Root 3 times root 2, we can make it root 6. So it's 2 root 6. You can cube it. Right. Okay, so you reduce the power from 6 to 3. And now you have a plus b all cubed. And that when you're cubing a sum, it's 5 cubed. Now I hope you know remember the formula for this. It's 3 times 5 squared. Okay, let me just remind you. A plus b all cubed equals a cubed plus 3a squared b. The powers of a come down. Again, you have another 3 and powers of a come down further, but the powers of b climb. And then in the end, you'll have plus b cubed. Right? So I'm going to do the same thing here. I've got 3, 5 squared, and you still multiply by 2 root 6 because we have to carry the b. And then you have a 3 in front. And now the 5 squared becomes 5. And the 2 root 6 is now squared. Right? And then finally, you go 2 root 6, which is cubed. So you got some complicated looking thing like this. Let's try to simplify this. 5 cubed is 125. 3 times 5 squared, you don't need a calculator for this. 5 squared is 25. 25 times 3 is 75. Times 2 is 150. You're not allowed to use calculators. That's a horrible thing about this. 3 times 5 is 15. 15. Oh no, here you're squaring this part here. So that's nice because when you square this, 2 is squared, you get 4, and this is 6. So 4 times 6 is 24. This part here. When you square it, you get 4 times 6, which is 24. And you're multiplying it by 3 times 5. That gives you another 360, is it? 120 times 3, so it's 360. That takes care of that. And this thing here, you're cubing it. So it's 2 cubed, which is 8. And the square root of 6, when you cube it, well, when you multiply it twice, you get 6. Root 6, and the third root 6 doesn't simplify. So this gives you 48 root 6, 8 times 6. So you have 150 plus 48 root 6. But the numbers are 125 plus 360, which is 485, plus 150 plus 48 is 198 root 6. Well, we have a 6th power, right? And you got these numbers. But now we still don't have our integer. We have to see what is this equal to. And you want to see the closest integer, the smallest integer, which is going to be larger than this. Unfortunately, you can find approximations for this. In fact, there's a very, very good approximation. The square root of 6 will be some number between 2 and 3, obviously. It'll be a number between 4 and 9. So it's 2 point something. You can try 2.5 and square it. You get 6,25, which is almost 6. But it's 2.5 is more than this. This is less than 2.5. But when you square 2.4, you get 5,76. So 6 is in between here. So the square root is in between 2,4 and 2,5. So a good approximation would be 198 times 2,45. That's halfway in between. That's halfway in between. Mind you, when you square 2,45, you get a very, very close answer. You get 6,0025, very, very close to 6. So you'll think, hey, I've hit the jackpot here. And when you work this thing out, you will see that you get 970.1, all this. When you can multiply this thing. You can do it long multiplication. 2,45 times 2 is 4,9. And then you multiply by 99. All this, you don't need a calculator, but it's all a lot of hard work. And you can work it out and you'll see that the answer is 970,1. But that still doesn't tell you if this, what is the smallest integer larger than this. You might say, well, I think it's 972, but you don't know because this is an approximation, you see, to that. It may very well happen that this thing here, when you multiply it by 198, it crosses 971. You don't know. So the problem looks very difficult if you try to expand this thing like this. So that is where the strategy comes in. And so this is how we do it. As I told you earlier, when you got numbers which don't look very nice, give a name to them. So we're going to let A be equal to this. And the problem is to find A to the 6th. Not quite. We don't want to find A to the 6th. We want to find the smallest number which is larger than A to the power of 6. That's a goal. Right? Now we have seen something like this before. When you have these multiplied like this, you can consider the number √3 minus √2. Right? That's an interesting number because when you multiply these two numbers, you get A plus B into A minus B. So it's nice to create a number like √3 minus √2 because you can do something with it. When you multiply these two, you're going to get √3 times A squared minus B squared. So you're going to get 3 minus 2, which is 1. Okay, which is quite nice because it means that I got a formula for √3 minus √2. This is A. This is A. So you got a formula for √3 minus √2, namely that this thing here is 1 over A. √3 minus √2 is 1 over A. I'm going to put that down here. 1 over A is √3 minus √2. Okay, and I'm just going to, A times this is 1. All right, now I'm going to delete I'm deleting this because I'm going to create space. So, and just repeat this thing wherever we had it. So 1 over A is √3 minus √2. Now, I want to get to A to the 6th. I want to get to A to the 6th. At this stage here, problem solvers will know something very useful. And it's a very, very important equation that involves a number. When you add a number to its reciprocal or to its inverse, if you like, this is also called the inverse. When you square this, right, you'll get A squared. But the middle number is this times 2. It's a nice number, 2. See? And here you have 1 over A squared. See? But what is A plus 1 over A? When you add these, plus 2 plus root 2 minus root 2 cancels. And you have 2 root 3. You're squaring that. That is equal to a squared plus 2 plus 1 over a squared. And that allows you to calculate a squared plus 1 over a squared. Because this here, you're squaring root 3, so you're getting a nice number here. You're going to get 4 times 3, which is 12. So this part here is 12. You take the 2 to the other side and you get 10. So we've got that a plus 1 over a is 2 root 3. I'm going to take out all these things now. I just want to hold on to this lovely answer here. I got that a squared plus 1 over a squared is 10. Now that gives me an idea that I can go on. Sorry. I need to get to a to the power of 6. So let me square both sides here. That will take me very quickly to a to the 4th. When I square both sides, what do I get? I get a to the 4th. The middle term is again 2. And the last term, when you square it, you get 1 over a to the power of 4. So when I square the left-hand side, I get this. And when I square the right-hand side, which is 10 squared, I get 100. So I can take the 2 to the other side, and I get a to the 4th plus 1 over a to the 4th equals 100 minus 2. 100 minus 2, which is 98. Right? So you can see I'm preserving these things here because I can now get to a to the 6th quite nicely. This is where I want to go to. So I'm just going to remove these calculations. I just wanted a to the 4th plus 1 over a to the 4th. I just calculated that to be 98. So now to get a to the 6th, I can multiply these two. Right, when I multiply these two, let's see. A squared times a to the 4th is a to the 6th. Now you can cross multiply this. A squared plus 1 over a to the 4th is 1 over a squared. A squared plus 1 over a to the 4th, there's 2 a's on the top will cancel. And if you multiply these, a to the 4th over a squared, which is a squared. A to the 4th over a squared. And then you multiply the last two, and you have 1 over a to the power of 6. So you can, what we are doing is multiplying those two to get to a to the 6th, and you multiply these two, you get 980. And we want to isolate just that part there. So you get a to the 6th plus 1 over a to the 6th is equal to 980 minus the stuff here. But we calculated this. It's 10. And lo and behold, you come to 970 again. Earlier on, we came to this number 970. And we said perhaps the highest, the smallest integer bigger than a to the 6th is 971. Now watch. A to the 6th is what we want to get to. It's 970 minus 1 over a to the 6th. Now that's very interesting. It means that a to the 6th is smaller than 970. So the answer is not 971. See? a to the 6 is smaller than 970. It's not 970. So the possible answer is 970. But we want to know, the only way you can say the answer is 970, it's the smallest integer larger than that. Only way is whether this thing here is smaller than 1. If this was say 2 more than 1, then you got a problem. So the question is 1 over a to the power of 6 less than 1? If it is less than 1, then you're subtracting a number which is smaller than 1 from 970. So you'll have 969 plus point something, right? And that will give you exactly what a to the 6 is. So therefore the answer would be 970. But I want to know whether this is less than 1. Well, let's go back to a and see what it is. If you want 1 over a to the power of 6, you need to see what, you're taking inverses, you need to see what a is greater than. You'll see just now why we're saying that. So what is a greater than? A is equal to root 3 plus root 2. And that is greater than, do we know anything that is greater? It's greater than something that we know. Well, it's certainly greater than, well, this is 1. Root 3 is greater than 1. And root 2 is also greater than 1, obviously. So a is certainly greater than 2. Which means that 1 over a is less than 1 over 2. Which is very nice, which means that 1 over a to the power of 6 is going to be less than half to the 6th. Oh, that's very small, 1 over 64. We wanted to know whether this is less than 1. It's actually less than 1 over 64, so it's extremely small. So the answer is this number is very close to 970, right? And it's a very small number that you're subtracting from this. So the smallest integer, which is larger than this, is 970. And we can say this with certainty now, because we know precisely. See, the roots have disappeared. We have nice proper fractions which we can estimate. Okay, so guys, I think that is quite a challenge, but you see that how you can use mathematics. The usual mathematics that you know, cubing, finding the cube of a sum, the square of a sum, and some indices and all that, various kinds of things, approximating, taking, if a is less than b, then 1 over a is greater than 1 over b, some inequalities. All these things which you learn, in school, you've hardly ever seen the applications of that. But here, we found a very beautiful application. In fact, I was very thrilled with this thing, because when I calculated the actual value of this, you wouldn't believe it, but this thing's extremely close to, it's extremely close to 970. This thing is actually 969. Oh, come on. It's getting too late in the day. I can't do simple things. Oh, man. Oh, I can't seem to be getting, but this is actually 969.998 or something. Very, very close, to 970. Okay, guys. So we did some rather challenging problems. I told you that you have to give me another possible hour, and you've actually gone on for 3 hours. And I'm very grateful to all of you who have stayed on till the end. Okay, so let me just stop the share. And we got 28 diehards, people who have lasted the marathon for 3 hours. Appreciative of that. And let me see what people have. Some people were chatting. So, okay, Joshua said, I have to go, unfortunately, but thank you, and so on. And so somebody else have to leave, and they said a sad goodbye. Hey, it's not really sad. We will continue to meet. After the second round, I'm going to continue to have these classes, maybe not as many, but then we're going to go on to more. We already had a couple of challenging problems, but when we meet again, we're going to be even, continue with challenging problems, and sometimes even more challenging. But most of the time, we're going to be looking at problems which occur in round 3, right? Because I'm going to prepare those people who have passed round 2 for round 3. But everybody is invited. All those who got to round 2 are invited, and you can still sit and enjoy some difficult problems which you think are very difficult. But when we see the solution, they say, I can understand the solution. So that's very nice. If you can understand the solution, it means that I could have got to that solution, but it would have taken me a bit of time trying on various things. Okay. All right. So any questions? Any comments? Anshu thanks me. No problem. I'm going to have a great weekend, Anshu. Any comments? People are exhausted now. No questions, Christian says. He says, thank you for the lesson. Okay, TK. You too. I will enjoy the afternoon. Okay, no questions. All right. Then shall we end the session? Okay, if anybody wants to remain behind, you can go. So all of you want to go, you can say goodbye and go. Bye, Daniel. Bye, Krishna Raj.
Thank you.
Okay, bye, Kopano.
Bye.
Sutirtha, bye.
Thank you very much, Prof. Enjoy the rest of your day.
Okay, so hey, Sutirtha, you one of the days we will meet face to face, because you've been in my classes for quite a long time now, eh?
Surely, Prof. I'd love to meet you face to face.
Oh yeah, oh yeah. Hopefully we will meet somewhere face to face so we can shake hands or rub elbows.
Surely.
Okay.
Thanks, Prof.
Hopefully we'll meet when we meet. We will be shaking hands.
Surely.
Okay. Bye, Nkosi.
Thanks, Prof. Bye-bye.
Okay, bye.
Thank you.
Okay, bye, Joseph. Have a nice weekend. Okay, Helen, you're still around. You got any question? Okay, bye everybody.